So Dr. Trainer, you have the floor.
Great, thank you. Very excited to be here and get to share with you some of the information about this really, really exciting mission, Dragonfly. Does everything look good?
Looks great.
Okay, good. I'll get started to try to get the windows out of my way. All right, so as I mentioned, I'm here to talk to you about Dragonfly. Dragonfly is a mission to Titan, which is a moon of Saturn, and I'll tell you a lot more about Titan and just why we even want to go there in the first place. But I always like to introduce this photo that is on the title slide. It's probably because I just think it's so beautiful. This is an image of Titan. And you can see its, parent moon in the background, Saturn, and almost perfectly edge on Saturn's famous rings. This is an image that was taken by the Cassini orbiting spacecraft, which is the last time we had any kind of spacecraft in the Saturn system. And I'll talk a little bit about Cassini. And this image of Dragonfly, you can kind of almost see a little bit of variation here in the surface, and the arrow kind of points to where it is we're planning to go with the mission. And you can see we call it a rotorcraft lander. You can see it here, but of course it's not to scale. It's not that big compared to the planet. So let's see. I always want to acknowledge members of the Dragonfly team. This is a team photo we took a year ago in November of 2020. We just had a team meeting and we were actually able to be hybrid. So some people in person and some people on Zoom. And we did take a photo, but it hasn't been, the photographers haven't sort of finished putting it together yet, but we'll have another photo of those team members. But these types of endeavors take really hundreds and hundreds of people working very hard. So this is just a small subset of the people on the team. We have scientists and engineers and technicians, and of course, all sorts of people working on the mission, really all over the world. And so it's like all things we do in the solar system, it takes everybody. All right, so let's talk a little bit about Titan. What we have this opportunity at Titan, it's a really unique place in our solar system. And I'm going to tell you a lot about it. That's going to make it sound very exotic, but I just want to set the stage that actually it might have a lot of really valuable lessons for us Earthlings. One of these has to do with understanding our past better. So we don't really know how life came to be on Earth. Right? We can't go back in time to study our own prebiotic history. And anywhere we go on this planet, pretty much anywhere you can go, there's an overprint of current biology, right? Life can survive in all sorts of places on our Earth. And so we look out into the solar system to try to understand and provide pieces of the puzzle to what types of places might be conducive for life, be habitable, places where life could be, as well as what kinds of processes and chemistries might be important to kind of go along that evolutionary path where ultimately chemistry takes the leap to biology. And Titan is actually one of the places we think might have some really important clues for that. It has some similarities to what we think the early Earth might have been like. When I say that, I'm talking about the Earth over 3 billion years ago. There are processes occurring in Titan's atmosphere and on its surface that could be relevant to the types of processes that could have occurred on Earth and may have been important. And again, the chemical origins that ultimately led to biology on Earth. And so we're very interested. We have the ability to go to Titan and study what those processes are like on a planetary scale without sort of that pesky life everywhere getting in the way. But more about Titan. Titan is the largest of Saturn's moons. We have 62 written here, depending on who you ask. There could be something like up to 80. It depends on whether you count every single, small rock that can be seen around Saturn. So the point is Saturn has lots and lots of moons, but Titan is by far the largest. Here you can see some of the other moons of Saturn, and Titan really stands out. In that, it also stands out when you look at it sort of with all the other moons in the solar system. So these are the other moons in size order. So when you start kind of all the way on the left of the screen, that's Ganymede. That is the largest of Jupiter's moons, one of the 4 Galilean moons, and it is the largest moon in the solar system. Right after that comes Titan. After that is Callisto, which is another moon of Jupiter, then Io, another moon of Jupiter. Following around, you see our moon. And then after that is Europa, which is another moon of Jupiter. So then we've now covered the 4 Galilean moons, and then goes on and on and on. So you can see where Titan sort of fits into that. But I also want to point out how Titan stands out from all of these other satellites. So one thing you may notice is that in all of the other images, you see craters, you see, what we might call scarring or lines, striations on the surface, because you are seeing the surface of the moons. And in fact, on Io, the very yellowish one, you even can see volcanoes, because Io is a very volcanic place. But Titan is different. In this particular image, this is sort of what, would look like to your visible eye. It's very fuzzy. It just looks like this fuzzy orange ball. And that's because it has an atmosphere, and that atmosphere is full of particulates, kind of like a haze or a smog type material. And that means we can't see the surface. And it's also, as you can see, it's the only moon that looks that way because it's the only moon that has a substantial atmosphere. It's one of its many unique things. Oh, and here are all my labels. I forgot we're there. We can look at Titan just compared to some of the other terrestrial bodies in general. Of course, Earth and Venus are very similar in size. Venus has, for all of the terrestrial bodies, so we're not counting the gas giants, for example, Venus has the highest surface pressure, so the most gas. It has about 100 times the surface pressure of Earth. Following after Earth, you have Mars, which has 1/100th the surface pressure of Earth. But Titan actually has about 1.5 times the surface pressure of Earth. So if you were ordering everything here in terms of pressure, or like how much atmosphere there is at the surface, or density of the atmosphere, you'd actually put it in between Venus and Earth. You can see also where Titan ranks up, and even compared to Mercury. Some more fun facts about Titan. The image on the left gives you the idea, I've kind of been describing of that sort of fuzzy orange ball, which is really us seeing all those particulates in the atmosphere and not seeing the surface. But if you look in the right wavelengths of light, you can see through that haze, and you can see to the surface. And that's that image on the right that was taken by the Cassini orbiter. The surface gravity is about 1/7 of Earth's surface gravity. And I mentioned that it has about 1.5 times the surface pressure. And when you factor in temperature, it's very cold on Titan. That's one of its most, I would say, defining characteristics when we think about what it's going to be like to be on the surface of Titan with this spacecraft. It's 94 Kelvin. That correlates to minus 179 degrees Celsius or minus 290 degrees Fahrenheit. So I keep hearing the Michigan folks saying that it's cold tonight, but that's nothing compared to Titan, right? Titan is extremely cold. And I also want to talk a little bit about that atmosphere. So the atmosphere of Titan is very extended compared to Earth. So not only does it have a higher surface pressure, it also kind of goes up higher. So the layers of the atmosphere on Titan are taller. So where, it's always a sort of a fuzzy line where you say that the atmosphere of Earth ends and space begins. But one common place that we define roughly that transition is maybe on the order of 100 kilometers on Earth. Whereas on Titan, that could be like 1,000 kilometers is sort of where you might find that transition. This image on the right gives you an idea of the relative scale of the things on Titan versus Earth. Just again, that idea that the atmosphere is very extended. So it kind of goes up taller. So you can see the y-axis is height in kilometers. And actually you can see, temperature kind of represented. Titan is in a much colder region than Earth. Titan has clouds. It actually has rain, all just like Earth, but you would find those clouds much higher in the atmosphere, whereas on Earth, they're much lower. And one thing I'll hint at, and we'll talk about this more, these clouds are not water clouds. That rain is not water rain. It's actually all largely methane. Titan is so cold that methane is right around its trickle point. And so you can get methane in a gas form. You can also get it as a cloud condensates and rain and rivers and seas. So where Earth has a hydrological cycle, Titan, we say, has like a methanological cycle, or something like that. And also Titan does have very small mountains, but of course Earth's mountains are much more pronounced. The interior structure of Titan, this concept comes from, again, all of the measurements that were made with the Cassini orbiter. You can see a little cartoon of the Cassini orbiter in relation to Titan. And the interior has some similarities structure-wise to Earth, but again, a kind of exotic materials. So there's a core, sort of a rock core, but then over that, we've sort of inferred from measurements that there's an ice layer and then a liquid water layer. So a liquid water ocean layer in the interior, but then over that again, an ice layer. And so when you think about Earth, right, we have the crust, which is made of rock. And then below that, you have the mantle, which is, liquid molten rock, or, the magma. And then the solid core underneath. And so for Titan, it's kind of like that, except that water ice really forms that rock, that bedrock. It's so cold at Titan that water ice is as hard as rock is on Earth. And then below that, that liquid layer is water, liquid water, perhaps with some ammonia in it, probably with a lot of other materials mixed into it. And so you can see that structure. It's like similar, but then different. Okay, so one thing also I want to talk about, why is there that haze there? I kind of referred to it as smog for anyone who's sort of familiar with the kind of smog that you can get built up in certain types of environments. And so the answer is, well, Titan looks that way. It looks like that fuzzy ball because there's very complex organic chemistry taking place there. And this is one of the things that really makes Titan stand out as a very interesting destination for our exploration. So I mentioned there's methane there. Methane is actually forms up to about 5% of the atmosphere is methane. The rest of the atmosphere is mostly nitrogen. Nitrogen is the primary component in our atmosphere and Earth as well. Titan and Earth are the only two places in the solar system where nitrogen is the major atmospheric component. And so you get energy from sunlight. And we also have some energetic particles that kind of exist in Saturn's, the environment around Saturn because of its magnetosphere, its magnetic fields. And those come into the upper atmosphere. They interact with the methane and the nitrogen there and some of the other, smaller species, and leads to dissociation of methane. You kind of break it apart and reform new molecules. And you can form very different hydrocarbons from the methane. You also include nitrogen in there, things like nitriles, and you can get bigger and bigger molecules, more complex structures. And eventually they can get large enough, they'll condense into particulates. So you get sort of aerosol particles, and those can all stick together. And that's what forms the haze. So then that haze material is basically complex organic material. And ultimately it's going to fall down and it's going to get on the surface. And it ends up, it could coat sort of the whole surface. So in a lot of places on Titan, on the surface, what we expect to find are areas where there's sort of organic, say dust or, whatever it was, sand almost, it might be. In certain locations over an ice layer. And the idea is if that has gone on and on for hundreds of millions of years, then there may also be times where the organic material and water can mix. And I'll talk a little bit more about how that could be possible. But it makes Titan a really fascinating place to go because you have this, complex engine of organic chemistry everywhere, right? You and I, we're all made up of complex organic chemistry. And so we know this is happening on a planetary scale. And so the question is, how far does that chemical processing get along towards maybe some kind of biochemistry, or molecules that could resemble things that could turn into biochemistry that we might recognize. But a little bit more about Titan's, just what it's like there, the seasons on Titan. So Saturn and Titan orbit the sun together, and it takes almost 30 Earth years for them to complete 1 year, which means the seasons, right, are a lot longer. It has Saturn's tilt is 26.7 degrees, which is not that different from our axial tilt at Earth. And so it does have similar seasons in terms of, summer, fall, etc. But those take more like 7.5 years to get through each season. And a day on Titan is 16 Earth days. And that's how long it takes to kind of fully rotate with respect of the sun. I put on the right side here, you can see just an idea of when some of these different seasonal transitions have take place, just to get an idea of the scale. So right now we're in between the northern summer solstice and the equinox. So it will be northern fall sometime in May of 2025. And then it won't be until 2032 when you get another seasonal change again. Just a little bit of background on the exploration of the Saturn system. I've been mentioned the Cassini mission several times. The Cassini mission arrived in orbit around Saturn. So it was an orbiter, or Saturn arrived in 2004. And there was actually a probe that dropped through the atmosphere of Titan and landed on the surface in 2005. And so we have a nice profile and some images from the surface that I'll show from that probe. And it survived on the surface on the order of 70 minutes before it end of mission for that. But then Cassini stayed in the system for an extremely long time, all the way until 2017, when it sort of plunged into Saturn. And so Cassini was orbiting Saturn and visiting multiple locations in the Saturn system, but it flew by Titan over 100 times. And a huge majority of the images and the data that I'm sharing with you tonight are all thanks to that extremely successful and wonderful Cassini mission. But I did neglect to mention, of course, prior to that, though, we had Pioneer and the 2 Voyagers did pass by the system and get images and information from Titan as well. This is an image of that Cassini orbiter here, and this shows the Huygens probe. So this is the probe itself inside of the air shell. These are people to help give you scale. The probe is pretty big, and this, I don't know if you guys can see my pointer, but if you look at the Cassini orbiter, the gold, there's sort of that gold rounded shield on the right side of it. That's that same probe that you see in the right-hand pictures. The Cassini was big, it's really big. There's kind of a desk chair in the bottom left of that image that helps give you scale. And here just shows the tour that Cassini made around the Saturn system. As I mentioned, there were 126 close flybys of Titan. So now let's see what Cassini saw. This is a sort of color enhanced map of Titan, where we looked at the surface in multiple wavelengths, as I mentioned, kind of through these windows where you could see through that haze, and put together this composite map. And the colors are meaningful in terms of they represent different types of compositional locations. So for example, those brown areas that you see versus the purple versus the white, those represent areas on the surface that have uniquely different compositions from each other. Now, we can't tell you exactly what that composition is. We don't know exactly what it is just because there's not enough detail in that spectral information, but you can tell that it's very varied. And just looking at this image, I'm going to point out some of the really interesting features that you can see on the surface, but you already kind of get the idea. There's a lot of diverse environments on the surface. There's different places you can go where you would encounter different materials and different environments. And all of those could be very important for understanding Titan and sort of understanding that question about what is that environment like and how could it support, this complex chemistry. So let's zoom in on a few of these. So one of my favorite things to look at in this image, and I hope it's coming through well with the color, are these dunes. There's these equatorial dunes on Titan, right? So they must be wind formed. You can see in this image, look at kind of like the black lines, gives you that sense of the dunes. And these dune fields, they're made up not of the kind of sand that we have on Earth, which is a silicate sand that comes from, weathered rock, but rather these are like organic sands. So the original material that forms sort of these organic sands is that stuff that's made in the atmosphere and that ultimately falls down. Now, it's not entirely known how you go from that very small particulate material that deposits from the atmosphere to the kind of grains that are big enough to then sort of stick together and form these dunes as they're wind blown. There's a couple of hypotheses. There's a couple of thoughts of how it could take place. But the expectation is it's sort of all related as part of this processing and this timeline of kind of experience that these organic materials can go through. If you look in the picture, you can see how the dunes kind of flow around other features, other tectonic features that are taken, just like they would on Earth, just like you would see sand dunes flow kind of around maybe a big rock or even, a building. Impact craters is another big thing you can probably zone in on. There's not nearly as many as you might find on one of those moons that has no atmosphere, for example, but you can see these impact craters. So a really big impactor gets through and it makes it through that atmosphere and it hits into that water ice crust. And if it comes in with enough energy and it's big enough, you can actually get melt of that water ice crust. And so this is one of the ways in which we could get liquid water present on the surface of Titan despite how cold it is. Because if you have enough energy coming in and you're able to melt the water with that impact, even though it's so cold on Titan, it can actually take a long time for it to freeze over. Depending on the size of the crater, it could be on the order of thousands of years, for example. There's also tectonic structures. I sort of mentioned very small mountains that are there. Again, these would be sort of places where the water ice crust forms, ridges and in other ways is sort of like squished together to form these types of features. And again, in this image, you also can see this one captures those dunes flowing around those tectonic features as well. There's a potential for what we call cryovolcanism. So this, again, the analogy of thinking of Earth and what a volcanic flow on Earth is, you can think about there's a connection between, the mantle through the crust, and you're able to get that molten rock kind of up and then erupting and then placing out on the surface of Earth. And you've probably seen some videos or images, or maybe you've been lucky enough to experience this in person, where again, the lava flows out of the volcano. And even though it's very hot and it's a lot cooler at the Earth's surface, it has so much energy and has so much heat, it still takes it a long time to cool enough to solidify back into rock on the surface. And so something similar could be happening on Titan. And there's a connection between the deep ocean through the ice crust, and you can get an eruption onto the surface of water, potentially water ammonia mixtures. You can get those things in placing on the surface. And again, it can take some time for them to freeze over. So that is another way in which you can have sort of transient liquid water environments on the surface. And again, it would be doing so on the surface that's coated in all that organic material. So here's an example of one potential sort of what we call a candidate of a cryovolcanic event. Here's another image, or from above, where you can see what looks like a potential flow coming out. Other really cool things, I talked about the liquid methane. Also, ethane is another big product of that atmospheric chemistry. You can get liquid ethane as well. And we see evidence of this in two places. One of my favorites are these polar seas. And they're kind of, when you look at the top of the picture, actually now, if you hadn't already noticed those black patches, right? So those are areas of liquid. And this is a radar image that shows everywhere where it gets completely black. This is a flat liquid surface. And so these are seas that are primarily methane, some ethane. This one here, that arrow is sort of, or the line is originating out of, that is one that is called Ligeia Mare. And that particular sea is about the size of Lake Superior. And then down sort of southeast of it, in this image at least, is another whole bigger sea system of lots of connected areas. And then we also see evidence on the more lower latitudes of channels that look like they have been carved by flowing liquid, which would be a flowing methane at one time. And this particular image actually comes from that probe that descended through the atmosphere, the Huygens Probe. We also see, even just observing both from the Cassini orbiter as well as other observatories, you can see evidence of the clouds, different weather patterns. And again, this idea that this methane cycle is similar to Earth's water cycle. It's just that on Titan, because you have these much longer seasons, and it's also further out from the sun, so there's less solar insolation hitting, everything is just going to be a little slower, so a little more sluggish. This image here shows the Titan landing, the Huygens landing site on Titan. So Huygens landed in what appeared to be sort of a dried out riverbed, kind of a plain here. And in the image, this orange image, you see those little pebbles in the foreground. Those things are on the order of, maybe 15 centimeters ish. But they're, it looks very much just like dust and like rocks. Maybe if you've seen a lot of pictures from the Mars surface, there's kind of a similarity there. But in this case, again, the materials there, these are probably pebbles that are round, sort of eroded and weathered and rounded, water ice blocks that are maybe coated in organics. And that surface could have a lot of, organic material overlaying on this ice bedrock. So again, seems familiar, yet very different. All of these exotic materials. And then just for kind of a fun contrast, next to it in this image, we have one from the Apollo landings on the moon, showing, an astronaut footprint, kind of roughly. That kind of shows the general scale of what we're seeing there with the Huygens image. So again, kind of pulling this all together, one of the reasons we're so interested in Titan is because we believe it's a place where you really can find all the key ingredients that are necessary for life as we know it and as we understand it. So to walk through again, we've got energy coming in the form of sunlight, as well as the chemistry that sunlight kicks off in the formation of those big molecules is really a way to turn sunlight into chemical energy. And then all of those, molecules deposit down, ultimately land on the surface. We have all this organic material. We have abundant complex organics. Exploration of Mars, for example, has been very focused on looking at sort of this more inorganic rocky land and looking for evidence of organic material and looking at for evidence of past organic cycles. Whereas at Titan, it's kind of the opposite, right? There's just organic material everywhere, and there's tons of this type of material. And then there's liquids. We talked about water. Water may have been available at certain times in Titan's past, for example, from an impact or potentially from cryovolcanism coming out on the surface. And you could have transient, and by transient, I still mean like 1,000 years of liquid water that's interacting with the organic material that's everywhere. And there's also this interior ocean. And then in addition, really, we have sort of two liquid environments. We have the methane. We have this active methane cycle. We have these lakes, these methane lakes. And again, I forgot to mention earlier, but Titan is the only place in the solar system besides Earth where you could go sailing on sort of an open liquid. There's no other place really where there's a body of, not even body of water, right? A body of liquid persistent on the surface besides Earth and Titan. So because of that, Titan is really the only place we can go to look at all of this rich chemistry and chemistry that likely has kind of started at least on its way to prebiotic chemistry, and do so in the context of this full planetary environment. And we have these Earth-like surface processes, but they're operating on different types of materials. And what does that mean? And what can we learn from that in terms of just whether it's how life originated on Earth or what the environment of Earth was like before life was there, as well as we look out even into the stars and we see other planets around other stars that might have places that kind of look like Titan as well. So we think Titan has really, really great keys to answer some of these very fundamental questions that we have, like what even makes a place habitable? Right now, we just know one inhabited place that we have evidence for, and that's Earth. And there's lots of different ways that a location can be habitable, and Titan is one possible, example. Also, what chemical processes could have led to the development of life? And then a big, big question that we have, I think that everyone has life developed elsewhere in our solar system? And, Titan is certainly one place to potentially look for that. Although I say Dragonfly is not set out, it's not a life detection mission, but we're very interested in learning a lot more about this fascinating place. So one of the keys, after everything we learned from Cassini and all of those different things, it became clear that you don't just want to go to one place on Titan to look for the answers of these questions. You want to go to multiple places on Titan because there are these very many interesting places. There's all these diverse materials. There's all of these processes going along. So the real challenge is, how do you do that? How do you get to multiple places? And how do you get scientific instruments that can help answer those questions to multiple places? Well, it turns out that the answer, at least the answer that the Dragonfly team came up with, is to use heavier than air mobility. And there's a lot of good reasons for that. And actually, I'm going to go to the next slides because I think it walks it through even better. So when you want to visit lots of places on a planetary surface, right, that can become a big priority for exploration. And we have a paradigm, right? And that would be Mars exploration. This is an image of the Curiosity rover, which has been on Mars for 9 years now. And the Perseverance rover has now been there for several months. And so that's what we do on Mars, right? We rove, we send rovers and we drive around, just kind of like you and I would walk around in a location or maybe drive our car to visit from place to place. But Titan actually has a big advantage over Mars in terms of long-term travel. And I hinted at it in the beginning. Titan's atmosphere is 4 times denser than Earth's. Its surface pressure is about 1.5 times, but then when you factor in how cold it is, the temperature, it actually makes it even denser. And so when you have a very dense atmosphere, sort of all forms of aviation are easier, whether they're lighter than air, like helium balloons, or heavier than air, like a rotorcraft, because it means you don't need as much rotor area to push against the air to give yourself lift. In fact, if you factor in that heavier pressure and then the lower gravity at Titan compared to Earth, so you just have less to push against, to lift yourself. If you and I had these wings, I forget what the exact span is, but maybe let's say like size of a school bus or something, we could flap and we could get ourselves off the ground because of the lower gravity and that dense atmosphere. So you can't do that on Mars because Mars has a very thin atmosphere. And as you've seen, there is a helicopter on Mars, the Ingenuity helicopter, but it's got very, very big rotors and just a teeny small body, right? Because it needs huge rotors to be able to generate enough lift. This is a cute cartoon that kind of illustrates that fact that it's much harder to fly on Mars compared to Titan and Earth. So with all of that, the idea is that on Titan, we can really cover a lot of ground because we can take advantage of this and we can fly. We can access geologic terrains that are actually tens to hundreds of kilometers apart over time by using this method of transportation. Just a couple highlights I wanted to point out about Dragonfly, because I usually get questions on these things. It is designed for the multi-mission radioisotope thermal generator, which is the same power source that is used by the Mars rovers Curiosity and Perseverance. Ultimately, the decision about whether we go forward by that is made by NASA. So this is sort of pre-decisional, but that's how we're designed to operate. You can't use solar power on the surface of Titan. The solar insulation is just not sufficient. So this gives enough power to charge batteries to enable the rotorcraft to fly. It's a dual quadcopter. So there's 8 rotors doubled up around. And just for scale, I wanted to show, this is actually a picture of the principal investigator, who's the head scientist and the head of the mission, Dr. Zibby Turtle from the Johns Hopkins Applied Physics Lab. And she's holding a prototype of those rotors. So you can see the size of about how big these rotors are. Dragonfly, this lander, there's not a scale on here, but it's sort of on the general scale of the Mars rover. So this is like taking the Mars rover and putting the helicopter and turning it into the helicopter, and it flies itself around. Also, I want to mention it has direct to Earth communication. In this image, you see its Huygens antenna deployed. And so there's not an orbital relay. There's not a whole bunch of satellites around Titan the way that we have built up at Mars. There's a very great infrastructure at Mars for that. And so we use line of sight communication between Titan and Earth, which means when it's night on Titan, when Titan's facing away from the sun, it means it's also facing away from Earth. And so we're in kind of a hibernation out of communication with the operations team on Earth. The timeline is to launch in June of 2027 and arrive by 2034. So that's a pretty good cruise. When we get there, we do direct atmospheric entry, so we don't go into orbit around Saturn first. And what's really cool about the timing, actually, is that we're going in at a similar latitude and the same time of the Titan year as the descent of the Huygens Probe. And so we already have data of what the atmosphere is like, what that profile is like descending through the atmosphere that has been very useful in our planning the entry for Dragonfly. And the cartoon on the right kind of gives you an idea of what that looks like. And come in, we slow down with parachutes, and we're in like an air shell, and it pops out that air shell, and then ultimately the rotorcraft comes out and can fly itself and do a first landing on the surface. Where's it going? So it's going to this place called Selt Crater on Titan. You can see this image here, but it's really landing first in one of those dune fields, those dune seas, where we can access that organic material that is forming those dunes, and also access these interdune areas where you can see stretches from, from what we've been able to measure from the flybys of sort of a water ice, exposed bedrock water ice. And then ultimately we want to traverse up into Celt Crater or, to Celt Crater to get to the materials that used to be melted water, where there had been melted water in the past that mingled with organics and now has frozen over, because we want to know what kind of chemistry took place at the time when it was water and what kinds of molecules can we find there. This is a picture of an analog on Earth that is somewhat similar to the dunes on Titan. This is from Namibia. This is the Namib Sand Sea. And so we're talking about dunes, but these aren't like the dunes, the small dunes that you kind of go up and down over the beach. These are big dunes, right? And that means the spaces in between the dunes are also very large. This lower picture here shows some of the Dragonfly team members and one of these interdune flats in between. And so this is just to give you the idea that, we're not trying to land this rotorcraft on really tiny dunes, right? There's big open flat areas between the dunes where there is enough sufficient flat and safe location for the landing, but then also the ability to hop kind of up over the dunes as well. The strategy exploration again is to go from about, where we land up towards the crater. And while we do that, we transition over multiple of these types of environments that we're interested in. And again, that's the organic sands made of the deposited organics, seeing the ice bedrock, as well as places where there used to be melted liquid water. The surface mission is on the order of about a little over 3 years. What we would call 74 Titan days, or TSOLs is the name for the Titan days of operations. And in the course of doing this, we would traverse something on the order of 180 kilometers and visiting something like 20, dozens and dozens of sites while we do that. I just want to talk about the way we do it on Titan, because it's just so clever and it's very interesting. So the way that we go as we fly, we don't have super high resolution maps of Titan. What we're going to do is we're going to kind of build up our maps as we go, using this leapfrog approach. So when we're at a landing site and we're ready to transition to a new landing site, that new landing site will be, say, a predetermined site. We'll get up, we'll fly over the planned landing site, keep going on more sort of reconnaissance and scouting out and getting images and building up maps of a new location, and then come back and land to the landing site that we originally planned. And then while at that landing site and doing all of the surface operations there, we'll look at all the data of the new area that was mapped and pick the next landing site. And then when transitioning to that landing site, do the same strategy, fly over it, scout out new area, come back, land at the landing site, and continually building up that map and figuring out where to land. I also want to emphasize that we show a lot of images, and I know I've got it up in my, Zoom background of Dragonfly flying and Dragonfly in the air, because that's one of the exciting things about it. But we really spend most of the time on the ground. So we might fly something for like 30 minutes, and that might happen every other TSOL, which means like once a month on Earth. So we really spend most of the science is done on the ground, but of course the flying is the key part that gets us to all of these new locations and helps us make sure that we're accessing the materials that we're most interested in. So what are we going to do? We have a lot of science questions. These are the major themes that we're going after. I've sort of emphasized the prebiotic chemistry one. We're really interested in just understanding what kind of chemistries have taken place and what kind of products are there. It's like Titan has been conducting these chemical experiments for millions and millions of years with all these organics intermingling with water ice and then liquid water. And we want to go see, what are the results of those experiments. Those are timelines that we can't access in a laboratory. We want to understand potential habitable environments on Titan. How does that methane cycle really operate? At least, in this regional area that we're going to be probing. And then the other thing we say is search for biosignatures. That really just relates to how do we interpret and understand the types of organic molecules that we do see? And do we start to see things that resemble molecules that we know are important for biochemistry, things like amino acids and nucleobases? Do we start to see the buildup of sort of complex structures that start to resemble, something like our biochemistry? We do this with a set of instruments. This is our payload. We have the Dragonfly mass spectrometer, and that's being built at Goddard Space Flight Center, which is where I am, and that's the instrument that I am the science lead for. There's also a sampling system which drills into the surface and delivers samples to the mass spectrometer. We have a geophysical and meteorological package called DragMet, and I'll talk a little bit more about that. A camera suite, of course, we couldn't go and not take lots of pictures and videos. And then we also have a gamma ray neutron spectrometer called Dragons. And so I'm going to tell you just a little bit about what each of these instruments is measuring. So first, I'm going to start with the cameras. I'm going to kind of go from when we land in a new site, the order that we'll be sort of exploring that area with the instrumentation that we have on our payload. So first, one very important thing is to put all the measurements that we take, any detail measurements we take, into context of where we are. And so this will be largely done with DragonCam, our camera system. And it's a system, it's very similar to what has been on the Mars rovers. And in fact, these images are images taken from Mars with cameras very similar to what we'll have on Dragonfly. And it spans everywhere from the panorama to kind of get the landscape of where you are, forward cameras, getting an idea of the land that you're on, downward, again, what are you sitting on when you land, down to the microscopic. So the microscopic camera you can see very small scale image of the areas where ultimately we may choose to drill and take surface samples. The picture on the right, we carry an LED array to let us illuminate the surface in a couple different wavelengths of light when we take images. And that's going to give us our first hint at the chemical diversity, the compositional diversity that we might see in a surface. And this particular picture was taken in a laboratory with a prototype of those LEDs, showing what it looks like when certain kinds of organics that we think are analogs for what we'd find at Titan are mixed with water ice. And you can see how the different colors pop out. And that's sort of the first hint that you have that kind of mixed surface. We can also use UV light to illuminate them, and certain organic molecules really glow, and they fluoresce very well when you hit them with UV light. And so that's another way we'll do an initial assessment of that composition. Now, DragMet, this is the meteorological package and the geophysical package. First, we can monitor the atmospheric conditions, do things like methane humidity, temperature, pressure, wind speed, actually look at amounts of hydrogen in the atmosphere as well. And then by sitting on the surface for long periods of time over the course of a long mission, we can really understand day to night variations. We can understand variations from place to place. We can get profiles, make these measurements as we go up and down vertically, and really build up a much better understanding of how the Titan sort of local, weather works, or just how does the atmosphere operate and how does it interact with the surface. We can also constrain the surface properties, things like how porous is it? Is it damp with liquid methane? Is that a place, where maybe you even can find what we would call a methanifer, which is like an aquifer, and get a little bit of information on the surface from some of those measurements. And then constrain processes that could actually help mix the subsurface ocean with the surface, things like seismic activity. And so actually there is a seismometer on Dragonfly. And so when we're on the surface and we're still, we can have the seismometer deployed and just be listening. And whether or not Titan is going to have Titan quakes that are big enough for us to hear, we don't know. That's a question for Titan. But if they're there and we can listen and we detect them, then we're going to be able to get information about the thickness of the ice crust and how deep it is down into the ocean. We also can classify the materials at every site with this gamma ray neutron spectrometer. So this Dragons is an elemental measurement, and basically it sends out energetic neutrons, and based on the interactions with the surface, what gets bounced back and measured relates to what elements are there. And so that can tell us things like, is there a lot of hydrogen and oxygen, aka water? Are we sitting on a big chunk of water ice? Or is there a lot of organic material there? Are we sitting in a big area of organic? And we can even see some layering. And that's sort of our first glance of putting in context each new landing site compared to the one before it. How is it different? How is it varying? And is this a place that we want to dig in and sample? The sampling system Draco is designed to operate in that really, really, really cold environment, right? The minus 290 Fahrenheit. Here's some cartoons of sort of prototypes that were used to demonstrate the process. Draco uses a drill to create powdered samples, and then it samples them pneumatically. So a lot like, a vacuum cleaner. It uses the fact that Titan has an atmosphere, a substantial atmosphere, and there's blowers that kind of suck up the material through tubing. And that bottom left image, you can see collects it in this cup. And then that cup is moved over and inserted in one of two interfaces or inlets to the mass spectrometer, which makes the compositional measurement. The compositional measurement is meant to measure a wide array of organic materials. This graph on the right, shows some chemical structures, and I know not everyone's super familiar with that, but the idea here is just to get that we can see a whole wide range of molecules, from some of the smaller amino acids all the way up to these really, much bigger structures. And we do that by using a couple different methods. We have one method called laser desorption, where I basically shoot the sample with a laser, and some large material can get desorbed and given a charge, made an ion, and then ingested in the mass spectrometer and measured. Or we can do something called gas chromatography, where we put the sample into an oven, we heat it up to a high temperature, and everything that comes off as a gas then transitions into the mass spec for measurement. And these techniques are things that have actually been matured for use on Mars as well. So we're taking the types of measurements that have been made on Mars to answer somewhat similar questions, and doing them on Titan. Put this one here, this amino acids is something we're interested in finding, and amino acids, among other molecules, have this quality called chirality, where they can look very similar and everything is made the same and connected the same, like your hands, right? Your thumb is next to your pointer, is next to your middle finger on both hands, but they're mirror images instead of, they're not superimposable, they're mirror images of each other. And for example, life on Earth, your body and my body, right? We only use left-handed amino acids. And so having an enhancement of like one version of a chiral molecule over another is thought as a possible, signature of maybe biological activity. And that's the kind of thing we can detect with this instrument if we find molecules like that at Titan. And then this is my almost last slide. So some current activities, right now we're in this really critical engineering designing phase, what we call phase B. We're doing all of the work to really understand. We're doing testing on prototypes, and understanding what it is we need to build and what the requirements are to get ready to properly design and build this rotorcraft to get it ready for launch. So here are just some images of the kinds of activities that are taking place. All the way on the left, this is actually the team that's building the sampling system, doing testing in a big chamber that is designed to operate at Titan conditions. So that means the 1.5 times Earth pressure and that minus 290 degrees Fahrenheit. So it's a very specialized chamber, and they did testing to prove that that whole drilling and suctioning and sampling all works in those conditions. In the middle, you're seeing we build these drone platforms to help test the flight software, because this is all auto navigation. The ground system sends a signal to tell the rotorcraft, okay, this is where we want you to go land, but all of the, takeoff, flight, and landing is all automatic. And then on the right is also an image from some testing that was done in a wind tunnel to really do some validation of the models that we're using to make sure that we understand how the air is going to flow around the rotorcraft while it's flying, and that helps design aspects of the flight system and the rotors and the power that's needed, et cetera. So Dragonfly, again, is designed for the exploration and discovery on what is really a world of two oceans, if you think about the water ocean and then the hydrocarbon oceans, really to understand how far has chemistry progressed in this kind of fascinating environment. And I will put this up just for a little bit, and I can also maybe put these in the chat. Here are some links to watch some more movies. I don't show a lot of movies in these virtual talks because they tend to be choppy, and often, especially if you don't have great internet, it's not that fun to watch a movie be really choppy. But I encourage people on their own time to go look at some of these great videos that really explain how it is, what it's going to look like when Dragonfly is on the surface. So with that, I just want to, I'm happy to take questions. I'll actually leave this up if people want to try to jot down some of these web addresses. But thank you so much for your attention.
Thank you very much, Dr. Trainer. That was a great presentation. I really enjoyed that. If anyone would like to ask a question again, you can ask verbally, but remember to unmute yourself, or you can put a question in the chat, and Bob usually reads those out.
Well, if I'm going to read them out, haven't seen any yet, but I'll ask my question first. It has to deal with the data transmission. If in 30 minutes, you're going to collect a ton of data, all these aspects of that planet, and then it's going to park for several days there. But what is the radio transmission time between the moon and Earth?
That's
I
very
know
question.
it's probably something on the order, what, 4 minutes or something like that?
Actually, it's 80 minutes.
80 minutes. Oh, okay.
So over an hour, that's how long it takes. And that's just for, that's basically how long it takes for one photon to get, right? So one packet of light to get from Titan to Earth. But in reality, the data transmission rate is, it's not great, right? You wouldn't be able to stream videos on Titan. And so it'll actually take a very long time to send the data back kind of bit by bit. So this is a place, where we do have challenges. And this is a place where it's unique compared to Mars. So at Mars, not only is Mars closer, but I mentioned Mars has all of these great orbiting satellites that serve as data relays. So they can take data from the spacecraft on the surface, the rovers, and then send it back to Earth over time. You can get multiple passes in the day. On Titan, we have that direct to Earth communication, and we'll have, every day an opportunity to send data back, but the rate will be slow. So when we do a drill and sample and measure the composition, it's going to take many, many days for that data to come back. Right now we're actually in that stage where we're starting to think about how that's going to work. We're understanding like what kind of data will we have, what's the prioritization. We're working on things like compression schemes, just doing everything that we can to get as much data back as we can.
Okay, I imagine you'll be giving new directions after you get your first samples back, and maybe you want to go back to the same place you were at before, or you're going to be sending directions from Earth back to the.
Yes,
the
right.
base,
Yeah, we'll uplink kind of new commands. Every time we communicate, it goes both ways, right? There's a downlink of data, and then there's an uplink of, okay, this is what you do next.
That's all. Well, I was going to, one last thing, it's all coordinated with the orbital characteristics between our planet and this moon. You're going to have some blackout periods, I suppose.
Yes, every time that it's Titan night is basically one big blackout period.
Right.
So we have, it's a 16 Earth day on Titan, right? That's for Titan to spin completely, 360 degrees. So we have 8 days where it's on and we can talk to it, and 8 days where it's night and we can't. And
right.
we can set up commands and it can do some activities, and then eventually it'll go into like a little hibernation until, we can communicate again.
All right. Well, thank you. But I don't see any questions on the chat at this point.
I had a question. You mentioned that earlier in your that the original probe that went to Titan didn't last that long. What protection do you have for a dragonfly to last?
Oh, yes. So I should just clarify, the probe was never designed to last very long. The probe was only designed to be an atmospheric probe that measured as it went down. And when it was that mission was conceived and the probe was built, we didn't know what the surface even looked like. All those images I showed you came after that probe, or some of them from the probe and the rest after. So it was unclear, based on everything we knew, there was a wide range of possibilities that could have included the whole surface being liquid methane, a whole liquid methane ocean everywhere. And so there were a lot of uncertainties. So it was only ever designed to last for a few hours, fall through the atmosphere. All its measurements were taken while it fell through the atmosphere. And the 70 minutes it lived on the surface was all bonus. That was like amazing, really great. And it ran on batteries. So the batteries were charged while it was hooked up to the spacecraft, and then it was ejected from the main spacecraft, and the power just was designed to last only so long. So with Dragonfly, I mentioned we're designed to use a much longer lived energy source. So we have batteries, but they get charged by that MMRTG power source. And that's why Dragonfly can live so long, is related to that power source.
All right, thank you very much.
Sure.
Dr. Trainer, I received a message in the chat that from William Dunker, who asked, what is the temperature of the liquid water layer?
Oh, in the interior? Ooh, that's a great question. I don't think we exactly know what the temperature is, but we can constrain it. It could be probably it's probably pretty cold, but it's warm enough to be liquid, but it's also under high pressure. And so, yeah, we don't know the exact temperature. I think that's a good question, but it's a lot warmer than the surface of Titan. Just like on Earth, you go down, it gets hotter.
Oh, Dr. Trainer.
Yes.
Yes, I mean, you appear to be young enough where you had the luxury of staying with this project until 2034, 2036, whenever it was. I mean, are you assured of being with the program, or?
I mean, I'm not none of us are assured of how long we'll be lived, right? But yes, so my role on the project, I showed you the picture of Zibby, who's the lead scientist, the principal investigator. I'm one of her deputies on that, and I'm also the lead for the mass spec. So the plan is that I will stick with this whole program until we land, and we have those 3 years of surface operations, because we're spending all this time doing the engineering work and designing the investigation, but really what I'm working towards is getting that data back, right? I used to, I do lab work where I look at these types of organic molecules that we think form on Titan. And so I'm most excited for when we finally get to use that sampling system and use that mass spectrometer, and we get the compositional information back, and then trying to interpret it and trying to figure out what it means. So that's my hope. That's the idea.
Well, good. Well, very good. Hey, Mark, then go ahead and maybe we can book Melissa for later on a few years down the road.
2037. Yeah. What does your calendar look like?
Probably pretty busy, actually.
Yeah, probably. Yeah.
All of those surface ops decisions.
In 10 years. Okay,
13 years. Yeah.
We have a question, comment from Ellen and Cheryl. Wonderful presentation. Secondly, David Kupfer to everyone was, how long before people can land on Titan? Thank you.
I guess I'd like to see them land on Mars first and see how that goes. Titan is much, much further, much, much colder. We've got a lot of technology development before we can think about sending people out to Titan.
Okay, any other questions?
I just want to say it was a great presentation. Thank you very much, Doctor.
Yes,
Thank
echo that.
Thanks for spending your Saturday night with me.
Oh,
yes, very, very good. Very informative.
Yeah, thanks for meeting with us.
Yeah.
Very detailed.
Martin Sampaio has a question in the chat. He said, could balloons be used for mapping on Titan?
Yeah, so actually there have been proposals to send balloons to do things like that. So, I showed you a lot of what you can do from orbit to really get these big global maps. And then what we're doing with Dragonfly, of course, is it's like really detailed, in depth. We're going to see that surface down to the microscopic scale. And balloons would kind of bridge that, right? So a balloon would be a way that you could get sort of big regional mapping on Titan. So people have proposed balloon missions to do that, to go kind of a Montgolfier, can't say it right, Montgolfier concept where, you can create a lot of buoyancy just with some heat, because Titan's so cold, that atmosphere is so dense, right? So you can create some buoyancy and float around, but it's a little bit harder maybe to control exactly where you're going, like compared to the rotorcraft. But when we were conceiving of this mission, ultimately what we came to is that what we most wanted to know next about Titan was, what is the surface made of? What are the chemical compositions? How is everything interacting, and what can Titan teach us, about what happens when you have organic chemistry happening on a global scale?
Okay, how long will it take to get there?
About 7 years on we don't know what rocket we have yet, but it's supposed to be a heavy lift grade rocket. So.
Well, hopefully they'll have the one they're working on now developed by then.
Yeah, well, I do hope that, that rocket is successful.
I think that was the best presentation I've ever seen. And I love the name Dragonfly. I don't know where they are now, but I loved dragonflies when I was a kid. So
yeah, I think that's when you've probably realized that a lot of NASA missions are acronyms, and not that many are just names. But Dragonfly is just the name. We just really liked it. We love the idea of like flitting around on the surface, sensing the surface, with all the tools that we have. And I think the name and it has a great logo too. I think, it helps sell the mission.
Oh, Dr. Trainer, maybe you mentioned it early on. Is the Dragonfly mission, is this strictly NASA, or is this a consortium of different countries?
Oh, that's a great question. So it is NASA. So NASA funds the program that selected Dragonfly. It's called the New Frontiers program. Missions like New Horizons to Pluto, the OSIRIS-REx that sampled the asteroid and is bringing back. Those are all fall under New Horizons. So NASA funded the mission, but we do have science team members, and we do have contributions from multiple other countries. So for example, the French Space Agency and the German Space Agency and the Japanese Space Agency are all contributing some hardware elements to it. So it's like a NASA mission, but we do have international participation. We're very grateful for that. We're very happy to have our fellow scientists from around the world.
Okay, good. Thank you.
Dr. Trainer, I have another direct to me question in the chat from William Dunker, who asked, how much does Dragonfly weigh? And wonderful presentation, he said.
Well, thank you so much. It's going to be similar to what the Mars rovers are like. As I mentioned, we're still in our design phase, so I don't have a final number, but you can think like hundreds of kilograms. That's, big. Good thing that Titan has that lower gravity, so it makes it easy.
All right, anyone else? Going once.
I have a question.
Mm-hmm.
Are there any other missions planned for like the other moons of Jupiter and Saturn?
Oh, that's a great question. Yes, great question. Thank you. So there is a mission actually that's going to launch sooner than Dragonfly called Europa Clipper. So that goes to the Europa moon of Jupiter. I mentioned was one of those Galilean moons. That's the moon it's got an water ice crust, and below it, we expect there to be a liquid ocean. And then below that ocean, we expect to find like a rocky core that has, energy in it. It may be like hydrothermal vent type things like we find on the bottom of our ocean. So that's another place we're very fascinated as a potential, a location to find life in the solar system. So the Europa Clipper mission is designed, it's going to orbit Jupiter and it's going to fly by Europa, and it's going to get lots of images of Europa. It's going to get information about the interior of Europa. It's going to really learn a lot about that moon. And then there's sort of concepts out there to take the next step after that would be to send a lander to land on the surface of Europa. And again, land there and make some samples, kind of like Dragonfly will, right? Drill into the surface, ingest it, look at the molecules that are there, and maybe even carry instruments like microscopes or something that can look for evidence of like microbes or things like that. And then beyond that, there's no other on the books. I almost forgot. ESA, the European Space Agency, is also sending a mission to the Jupiter system called JUICE. And that's also going to orbit Jupiter and fly by several of the moons, but focusing a lot on Ganymede, that largest moon. So we've got Clipper and JUICE will be there, maybe a Europa lander in the future. And then beyond that, there's thoughts of sending missions to another moon of Saturn called Enceladus. Enceladus is a moon that you may have seen pictures. It's got these really cool ice jets. It has these like geysers, so it spits ice particles out of its south pole. I love it. And Cassini discovered this. And so the thought is, well, you could like fly by there and scoop up those particles and measure them. And maybe, that's coming from an interior, a high pressure interior ocean. And maybe, find out what's in that ocean. Is that a potential habitat for life? So there's concepts to do that, but nothing is on the books for NASA. Yeah. But we have
cool. Thank you.
Yeah.
Very nice presentation.
Thank you.
Oh, I had one last question. What about international cooperation, other countries?
Oh, for Dragonfly or just in general?
Or just in general?
Just in general. Yeah. Well, working together with other space agencies is actually one of the best ways that we build international relationships, right? So these missions that we do, the big missions, really require more than one country's resources. So for example, I just talked about Europa Clipper and JUICE, and they'll both be kind of in the system at the same time, and can kind of build off of each other. And there's a lot of communication between those groups. On Dragonfly, we have international contributions. Sometimes on international missions, we have US contributions to those. So next summer, we should be launching another Mars rover, but this is run by the European Space Agency. It's called the ExoMars mission, the Rosalind Franklin rover. And there's an instrument on that rover that was actually built in the group that I'm in NASA. And in fact, the instrument we're sending on Dragonfly is similar to that one. And so that's one where we have a big US contribution on a European mission, for example. So the collaboration is so important because especially these really ambitious projects that we have, it's hard for just one country, to fund them. Anything else?
Nope, I'm just,
Okay.
Thank you.
Well, wait, there was a, I'm seeing one, Martin Sabhao is asking, are there plans to send a submersible probe to Titan to explore the ocean depth underneath?
Yeah, so I was just listening to one of my kids' podcasts that they like. We're just talking about the Titan submersible submarine. So that's another thing, what I would call, it's a concept. So that's an idea. In fact, one of the scientists who worked on Dragonfly also works on that concept development of the submarine, to go right to those seas and go underneath and look at the surface and understand that sea environment better. So that's again in the sort of the concept phase.